Now the first case is that is area under simple curve. Here we will discuss different cases. So before discussing area under simple curve, we will define a property of continuous function that is a continuous function defined on a closed interval attains maximum value at some point of interval as well as minimum value at some point of interval. That is, a continuous function must have a minimum and maximum value at some point of the interval. So on the basis of this, we can find out the area under curve. So we are going to discuss first case that says that case 1, curves which are entirely above x-axis. So let f be a continuous function defined over a closed interval AB and assume that f of x greater than equal to 0 for all x belongs to AB. So we are going to draw the graph of or diagram of that function. The function is that is this is the x-axis, this is the y-axis, and this is our curve y is equal to f of x. So we have to find this area. So this area is in between, that is we want to find area A enclosed by the curve y is equal to f of x and x is equal to a, x is equal to b and x-axis. That is, if you see, this is x is equal to a, this is x is equal to b, this is x-axis and this is the curve y is equal to f(x). So we have to find this area A. So by the definition of definite integral. Therefore, A is equal to A to B, that is x from A to B, f of x dx, that is y dx. Now, consider the second curve. That is, it may be of that shape. Y is equal to f of x is equal to a, x is equal to b, and area is a line between x-axis and x is equal to a, x is equal to b, and y is equal to f. So, diagram may be one of these two. So, area under curve, both the curve is a is equal to a to b, f of x dx. Now, we have to find the area between them. So, how can we find out? We will learn and we will study how can we do that. So, first of all, we divide closed interval AB into n sub-intervals determined by endpoints, that is, starting point is x0, that is A, then x1, x2, so on up to n, xn, that is the end point, that is B. Since f of x is continuous, therefore, it is also continuous on each subinterval. That is x of I minus 1 to xi, and I is varying from 1 to n. Then there exists a point xi dash which belongs to subinterval xi minus 1 to xi, such that f of xi dash is the minimum value of f of x in this subinterval. Let delta xi is the difference of, that is the length of subinterval. Then we construct rectangle with f of xi dash as its height and delta xi is breadth. That is in the figure. Just see, this is the x-axis and this is the y-axis and this is the origin. And we have the curve like this. that is x is equal to a, x is equal to b, and y is equal to f of x. So, for this is the interval that is xi, and this is x of I minus 1. So we have a point in between them such that is any interval, such that f of xi dash is the minimum value, and we have to construct the rectangle with that value. This is a rectangle. Now we have to construct more rectangle. And here A and B. So if we take the sum of these rectangles, that is the sum of areas of these rectangles is clearly less than the area A of the curve lying between y is equal to fx, x is equal to a, and x is equal to b, because we are taking here just the length f of xi and breadth delta xi. So, sigma I1 to n f of xi dash delta xi less than equal to a, because if you see in this part, this is a rectangle. So this part is remaining, this part is remaining. So this area is less than the total area. So this all sum is less than equal to A, and this is named as lower sum because it is dealing with minimum value. Now we will take similarly, there exists a point xi double dash belongs to interval xi minus 1 to xi such that f of xi double dash is maximum value of f of x in this subinterval. And let delta xi again same xi minus 1. Then we construct rectangle with height f of xi double dash and delta xi as breadth. That is, if you see in the diagram, that is x-axis and this is y-axis, this is origin, and we have the curve y is equal to f of x, x is equal to a, x is equal to b. Then we construct the triangle with maximum height and we construct the triangle of that height. So if we see, this is the extra area. So we can say that then the sum of area of these rectangles is clearly greater than the area A, which we are trying to find. That is summation I1 to n f of xi double dash delta xi greater than equal to A. That is number 2. That is called upper sum. So from 1 and 2, we have sigma I1 to n f of xi dash delta xi less than equal to A, which is less than equal to sigma I1 to n f of xi double dash delta xi. As delta xi tends to 0 implies upper sums and lower sums tends to a common limit. Because function is continuous. If a function is continuous, then limit exists. Then upper limit is equal to lower limit at the value of the limit. And it can be written as A is equal to limit n tends to infinity sigma I1 to n f of xi dash delta xi, which is also equal to limit n tends to infinity sigma I1 to n f of xi double dash delta xi. And also this can be replaced by definition of integration, that is A is equal to A to B f of x dx. That is by definition of limit as a sum. As a limit as a sum, we have A to B f of x dx is equal to limit n tends to infinity sigma I1 to n f of xi dash f of xi delta xi. So area between the curve is find out by A to B limit over the curve, that is f of x dx. There are also different cases. These are discussed in next lecture. Now we are going to discuss the case 2. Curves which are entirely below the x-axis. So in this form, we have the curve like that. This is the x-axis. This is the y-axis. This is the origin. And we have to find the curves below the x-axis. That is just like that curve. Y is equal to f of x below the x-axis. This is x is equal to A, this is x is equal to B, and this is x-axis. We have to find this area. So if we see, if the curve lies below the x-axis, then f of x less than 0, that is y less than 0, and x is varying from x is equal to a to x is equal to b. Then the sum defined in earlier part will be negative, but the area bounded by the curve y is equal to f of x, x-axis and the lines x is equal to a and x is equal to b is positive. Therefore, area is equal to modulus of integral I, that is modulus of a to b f of x dx. So this is the case when the curve lies below the x-axis. Now the next is case C. Curve which intersects x-axis at one point. That is, we will see in the diagram, this is the x-axis, this is the positive y-axis, this is the negative y-axis, this is the origin. So we have curve intersect x-axis at one point. So this is the one point, take it as c, 0, y coordinate is 0, this is x is equal to a and this is the line x is equal to b. So we have to find the area between these. So we can same rule by drawing diagram, rectangle here. So let the graph of y is equal to f of x intersect x-axis at c, 0. That is the only point where curve enters the x-axis. Only point C, that is lying between a to b. Let f of x greater than equal to 0 for all x belongs to a to c. That is the case of number 1. And f of x less than equal to 0 for all x belongs to c to b. That is the case number 2. So then area of the region bounded by y is equal to f of x, x is equal to a, x is equal to b and x-axis is given by a is equal to modulus of I1 plus modulus of I2, where I1 is equal to a to b f of dx and I2 is equal to a to c f of dx and I2 is c to b f of dx. So this was all about when the area under the curve and between the x-axis and the line x is equal to a and x is equal to b. And in the next lecture, we will discuss the different cases what happens when curve is x is equal to gy and we have to find the area between the y-axis and the given curve.